Hello everyone, my name is Zhou Chin Chin, currently pursuing the PhD degree in School of Informatics from Xiamen University. It's my honor to present our work called Training Free Transformer Architecture Search. Firstly, we would like to introduce the concept of transformer architecture search. Transformer architecture by the good performance of the manually designed VITs. And transformer architecture search aims at searching multiple configurations of VIT architecture in an automated way. So why do we try to implement transformer architecture search in a training-free way? Firstly, the VIT search space far exceeds the magnitude of CNN search space. Secondly, existing TUSH methods are time-consuming. Therefore, we try to base on a zero-cost proxy to complete the TUSH by ranking the VITs by the proxy in a training-free way. We depict the framework of the zero-cost proxy-based TUSH in follows. In this work, for the first time, we investigate how to conduct TUSH in and devise an effective training-free TUSH, TF-TUSH, scheme. TF-TUSH combines the synaptic diversity of the MSAs and synaptic saliency of the MLPs as a DSS indicator in evaluating VIT architectures. In the methodology section, we introduce the synaptic diversity in MSA and synaptic saliency in ALE. Firstly, the rank collapse of MSA indicates the diversity of MSA plays an important role in transformer, and under some constraints, the rank of the parameter matrices could be used as a measure of the diversity information in MSA. However, the rank of the MSA's weight matrix is difficult to obtain. Therefore, approximation of the MSA's weight matrix as the diversity information in MSA. The rank of the MSA's weight matrix could be approximated by the nuclear norm of the MSA's weight matrix to approximate its rank. Formally, the synaptic diversity of MSA is defined by the Hadamard product of gradients and weights. The MLP and transformer. It has been pointed out that the pruning sensitivities of MSA and MLP are different, and the concept of the synaptic saliency from the pruning community can be used as a proxy to indicate the performance of a specific module. Motivated by these findings, we analyze the pruning sensitivity of the different modules in search spaces, which indicates the MLP is much more sensitive to the pruning than the MSA. Therefore, we try to use the synaptic saliency of MLP as the proxy of MLP. Finally, combining the synaptic diversity of MSA and the saliency score of MLP as our DSS indicator. Based on DS, we designed training-free transformer architecture search method. In the experiment section, we present several main results of our method. The search results on autoformer and PIT search spaces indicate the generalization of our method among two different search spaces. More importantly, the search cost of our method is 0.5 G, which is much lower than the other transformer architecture search methods. The transfer experiment on detection with COCO dataset and the results on downstream classification datasets indicate the transferability of the searched optimal VIT networks. To conclude, for the first time, a training-free transformer architecture search method with an effect proxy is proposed. Based on a modular strategy, the synaptic diversity on MSAs and the synaptic saliency on MLPs are combined as a VIT-oriented performance indicator, i.e., DSS indicator. The random search guided by our DSS indicator achieves a competitive performance among different popular VIT search less cost. It merely takes 0.5 GPU days to seek relatively optimal VIT architecture, compared with 24 GPU days by the existing counterparts.